Hi, everyone. Welcome to Foresight's Neurotech seminar series. We're really excited to have Sumner Norman here from Neuroforest. And Sumner has been a repeat guest on the seminar series. Last time he gave us an outlook of what the next generation of BCIs, what we can expect from them. And it was one of our most watched and most cited and most attention-grabbing seminars that we had in the Neurotech series. I received so many emails afterward just from people wanting to learn more, want to get connected to you and so forth. So we're really excited to see what you are cooking up now. Today, you'll be discussing neurotechnology in particular for mental health, which is something that Neuroforest is focusing on now. And I'm really excited to have you on, and I'm sure that we'll hopefully try to leave some space for Q&A in the end. So once we hit the Q&A, you can just raise your hand. All right, without further ado, Sumner, it's a total delight to have you back on. Please take it away.
Awesome. Thank you so much, Allison. That's really kind. It's great to be back. I'm seeing a lot of familiar faces in the chat, which is always nice. So with that, we'll just jump in. As Allison was alluding to, I'm the co-founder and CEO of a group called Forest Neurotech. We are a hybrid nonprofit startup neurotech company, which I can get into a little bit later. But our aim is to create the first implantable device that's capable of both imaging and modulating function throughout the entire human brain without ever actually touching that brain. If we're successful, the result of that is that we enable a platform where you can actually develop neurotherapeutics in software, lowering the barriers of entry, accelerating development, things like that. And I'll come back to this in a bit. So I'm bringing this concept up early, but I'm actually going to set it down for most of the talk and come back to it towards the end, because I want to give a little bit of context on why I think this is actually such an important problem to be working on. So when most of us hear the word neurotech, we tend to think of headlines of Neuralink or videos like this one that I'm guilty of sharing multiple times, including the last time I was here at the seminar, of early intracortical brain-machine interfaces. And this is actually my co-founder, Tyson Aflalo, working with one of his first patients at Caltech, Eric Sorto. Eric has paralysis from the neck down due to a spinal cord injury and had for 13 years prior to this video. But as you can see here, he's drinking a beer of his own volition, which is a pretty cool thing. And so you see these magical moments with neurotech throughout these types of demos. This is a more recent example from the Stanford site of the BrainGate group. So they're doing imagined handwriting, and this kind of represents the current state of the art in BCI communication speed. The basic idea is the person's literally attempting to write the letters with their hand, but being paralyzed, they're unable to. And we can use that same electrode-based implant to listen in on single neurons in motor areas of the brain, and then effectively decode the trajectory of those hand movements, reconstructing the letter and eventually words and sentences and so on. Although these types of BCIs tend to capture a lot of interest in headlines and have really amazing demos, the majority of neurotechnologies that are actually in use today in clinics, in patients, are actually much, much simpler devices. So I'm going to spend a lot of time today talking about deep brain stimulators. That is because they are already implanted in over 100,000 people. So as just an example, this video is showing how DBS can effectively stop the tremor that's associated with Parkinson's disease. And it's just a pretty striking example from top to bottom. You just turn on this device and this person's tremor is effectively gone. DBS electrodes, for those of you that aren't as familiar with them, are implanted, as the name suggests, deep into the brain. Often you'll have two leads, one on either side of the brain, and you have a drive line that runs up through the neck and scalp from the chest where you have an implanted neurostimulator that's powering those electrodes. So we talk about the drawbacks of deep brain stimulators all the time. They're super invasive. They require a very talented surgeon to place them correctly. But this is actually the entire story. I think one of the lesser talked about reasons that we don't see wider proliferation of neurotech like DBS is that it only addresses this one aspect of the disease. So I'll expand on this in a second, but just to build on that video we just saw, Parkinson's disease alone has a host of symptoms that are associated with it. So balance, speech, mood, cognition, and of course, the motor aspect, tremor, which we saw before. So yes, DBS can address the motor system, effectively treat the tremor, but it's not touching on these other deficits. So even within a single disorder, we can see that the technology that's available in today's clinical neurotech is still fairly specific in its therapeutic effects. If you take that a step further, there are an absolute ton of potential diseases, disorders, injuries, and use cases for neurotech. So I've adapted this from my friend Milan Cvitkovic. I can't take credit for this long list, but I think it gets the point across that there are a lot of potential uses for neurotech. If I highlight just the ones that have a strong presence of a motor deficit associated with them, there's not so many, but not so coincidentally, these are the ones that you tend to hear a lot more about when you hear about advances in neurotech. That's because these are the things that neurotech can address today, the motor system. But again, even within each of these conditions, the device may only be addressing one aspect of the symptomology. So, although I titled this talk Neurotech for Mental Health, maybe the more appropriate title is really Neurotech Beyond the Motor System. That's where I'm really interested. As some of you know, and as I did at my last Foresight seminar, I find that historical context can give a lot of insight into why a certain technology evolved the way it did, including all of its strengths, all its faults, its shortcomings. So I'm going to start with a brief history of neurotech for mental health. And I ended up in a really deep dive myself on this. So it's pretty fascinating, I think. That will then bring us up to speed on today's neurotech, what it can do, what it can't, and then back to where we started. Tomorrow's neurotech, what's in the pipeline now? Where are we headed in the next 5 to 10 years? And what are the remaining challenges ahead of us? All right, so let's start at the very beginning. Maybe the oldest example of a quote unquote neurotech, it's a hole in the head, which may not sound particularly sophisticated, but I want to convince you that it actually is. So we're talking about prehistoric human beings in the Neolithic period, like 10,000 years ago. So modern anthropologists have actually found these skulls that have holes drilled into them, and that those holes have subsequently experienced bone growth before the person had died. So that means that they lived past this trepanation surgery. And this isn't just like an isolated case of one skull. There are many of these. And just to give you some context, even today, when a person has a traumatic brain injury, the state of the art is to take a portion of their skull out to relieve the pressure that's associated with that injury in a safe way. So it's thought that the Neolithic people doing this were thinking that they were letting bad spirits out. A person had fallen, hit their head, now they're acting very strange. They're possessed. We must let the spirits out. But regardless of the why they did it, I think the most amazing thing here is that we know today that if you put a hole in the skull, if you go through the dura mater or into the brain, that is almost certainly going to mean death for a Neolithic period, especially in an era that did not have antibiotics or ways to treat infection. They knew what they were doing to some degree. So that's the earliest form of neurotech. It would take several millennia before our understanding of mental illness would progress from one that focused on these kind of supernatural and forces and divine punishment. And the striking leap, as he always seems to appear, was from Hippocrates. So he proposed for the first time that mental health disorders had physical rather than supernatural causes. So you can see him here saying it's your brain, not demons, probably. And that was Hippocrates, probably. But in addition to saying this, he not only did that, but he started to classify what these disorders might look like. So we see some that we're familiar with, like paranoia, panic, epilepsy, so on. So this is a fairly advanced way of thinking about mental health disorders up to 2,400 years ago. So now I'm going to jump another couple of millennia forward. We're in the 16th century now. And so here, the Swiss alchemist Paracelsus actually started purposely inducing seizures or convulsions. And he did that, as he put it, to quote unquote cure lunacy. Now we have different names for that now, but the technology here is starting to look a little bit like the modern era. And I'll come back to that. But he was using a compound called camphor, which is derived from trees. And if you give it in large enough quantities, can cause these seizures. It might not seem like much, but this is really the spark that kicks off a revolution in what was to become electroconvulsive therapy for mental health. And that brings us into the 20th century. So now we're in 1938. Italian psychiatrists Ugo Treletti and Lucio Bini introduced the ECT as we know it and recorded their findings, sharing it with the community. And I put that as an important thing because I guess there was actually a case of Romans using electric eels on people way back when, but it was really hard to find specific details on that, so I left it out. But anyway, they recorded their findings, they performed ECT, and this really becomes one of the most effective neurotechnologies to date. And they were using it for severe depression. And then, of course, the use cases expanded from there. And although ECT these days still has a little bit of a controversial reputation, I was actually surprised. I didn't know the number. I know it was still used today. I didn't realize it's over 100,000 people per year still get ECT therapy. So it's still being used. So this is fairly modern. Okay, I'm going to come back to the physical tech in just a minute, but I feel like I'd be remiss, or it would be an omission not to take a brief pit stop and mention what you could call the most successful form of neurotechnology ever created by a very long shot. And that's pharmacology. In 1952, they discovered thorazine, and that leads to the effective treatment of schizophrenia. And this sort of kicks off a whole host of different antipsychotics, antidepressants, and other forms of psychopharmacology. And this is still the go-to treatment for most forms of neuropsychiatric and cognitive disorders. Of course, despite this boom in creating drugs, we are still experiencing a mental health crisis today, and it's been 70 years, so we know that drugs are not keeping pace with the needs. With that, we'll go back to neurotech or hard neurotech. And this is where I think it actually gets pretty exciting. This is where it starts to look a lot like modern day, and we start to see the kind of sparks of why things are the way they are. Throughout the 1950s and 1960s, Robert Heath, who I'm showing here on the right, he was a physician at Tulane University. He starts implanting electrodes deep into the brains of humans. So he's confident that you can use electrical stimulation to treat basically every psychiatric disorder out there. And he does end up being among some of the first examples that successfully stimulates the brain in a targeted way, where the stimulation is specific to the indication. So unlike ECT, where you're hitting the entire brain and hoping for a good effect, he's actually targeting specific brain regions, observing the effect, and updating his practice. So he ends up showing proofs of concept in schizophrenia, treatment-resistant forms of depression, drug addiction, and a whole host of other things. I do want to put a bit of an asterisk here, a disclaimer, that if you look up Robert Heath, his name and work drops off the record for decades, and that's because he ended up conducting some pretty controversial experiments. It's far too big of a topic for this talk, and I don't want to derail, but if you're interested in the philosophical dilemmas of developing a therapy that can just induce pleasure in the brain, you should look up Lone Frank's book, The Pleasure Shock. It's very good and very interesting. Anyway, so Dr. Heath, he's using this kind of incredibly complicated equipment. I'm showing his lab setup on the left here, and it's multiple rooms and recording equipment, stimulating equipment, and cameras. It's a big setup. And although the effects, and I point this out because the effects of the stimulation are rarely permanent. So you might have a reduction in your schizophrenia symptoms for a day, or if you're lucky, a few weeks, but eventually that's going to wear off. And so once you leave this very big lab that you can't take with you, that cure goes away. And but lucky for Dr. Heath and patients worldwide, something fortuitous was about to happen. So 1958, I'm actually going to leave neurotech behind for a second because OK Senning is a doctor that creates the first implantable pacemaker. And this is also just a fascinating story because the first one was put in secret, effectively. It was not an approved clinical study or anything like that. It was basically a patient who was desperate for a solution, and this doctor agreed to do it, which is pretty crazy. It was not only successful, the patient actually went on to have a series of pacemakers put in for their heart, and they actually came to outlive Dr. Senning, so they lived a long, healthy life. People like to talk about these early pacemakers or early medical technologies like they were these barbaric things, but I actually thought it was pretty interesting that even this early, literally the first pacemaker was fully implantable and included wireless charging, even though you had to recharge it once a week. Pretty amazing. Of course, it was cast in a shoe polish tin, so yeah, some things were maybe a bit in need of updates, but still pretty cool. Okay, why am I talking about pacemakers in a neurotech talk? It's really because market forces take over here. So Medtronic, they begin marketing this pacemaker for the heart through the 1960s. And even though it's not really built for the brain, neurologists start seeing the potential for this because people like Robert Heath are putting electricity into the brain at a particular frequency and it's causing an effect. And that's effectively what a pacemaker was designed to do. So now you have what looks like an entire lab in your pocket. The first one to really record positive results of this was in 1967. There was this Wisconsin-based physician named Norman Shealy. Great name. He was the first surgeon to adapt a cardiac pacemaker, and he did it for chronic pain and he did this with a spinal cord stimulator. So he takes several electrodes, puts them in the spinal cord of 5 different patients, and connects them to one of these Medtronic pacemakers. He had to modify the pacemaker to accommodate the higher frequency that you need for the central nervous system, but otherwise these devices are fairly standard. I don't know exactly which stimulator he used, by the way, but I'm showing this one on the bottom that came out probably a few years after this because this is the 1970s. But I just wanted to point out that some of these early pacemakers were nuclear powered, which I think is just the coolest thing ever. And they were made with plutonium-238 and a thermoelectric coil, and they could power a device for an entire lifetime, which is not something that is available today. So I just thought that was very cool. Anyway, back to it. So this is an example where market forces drive a technology down into a miniaturizable, implantable system, and that effectively creates this kind of lab in your hand. Taking a brief pause from stimulation, right around the same time, brain imaging comes onto the scene. The first one was CT scans in the 1970s, followed later by MRI and PET scans. And this, for the first time, allows for non-invasive viewing of the brain with this really kind of incredible detail. And even the first CT scan, this is literally the first one I'm showing on the right here, is pretty striking because you don't really need to be a trained neurologist to pick out that big dark circle on the left. That's a tumor. So these technologies, even right from out of the gate, were pretty crucial in understanding neurology and the kind of underpinnings of mental disorders. But I would argue that they're still underutilized in guiding stimulation. And I don't think that's because people don't recognize the potential value. It's just prohibitively complex. It's expensive for most groups anyway, if you want to stimulate the brain while the person's sitting inside of an active scanner. And unlike stimulators that are now implantable on our timeline, you can't take one of these scanners home with you. So there's a limitation there. Okay, going back to stimulation, while we've been talking about CT scanners, people have been busy through the 1970s. And through the late 70s and early 80s, we see positive results across all sorts of indications: epilepsy, cerebral palsy, tremor, schizophrenia, depression, Parkinson's disease, dystonia. And now it starts to feel like Robert Heath was right, like DBS can do everything. But for those of you that already know this, DBS isn't used for all these things today. It's used for the ones in red, epilepsy and Parkinson's disease, and then a couple others that I'm not showing here that were developed later for essential tremor and obsessive compulsive disorder. So the question is, what happened? Why are we not seeing DBS everywhere? These patient populations are big, some of them up to 700 that we're talking about, even in the early days. It wasn't a technology problem. This was a medical device regulation problem. So I'm pretty sure there's a real video on the right of the FDA to asking scientists if they're sure about their findings. But they basically come in and say, if we're going to approve a device for market, we need a very specific target and objective, measurable outcomes. And that objective measure tends to be the one that really trips up neurotechnologies for mental health. I found this quote from an early neurologist using DBS. I think it sums it up pretty well. He says, a major problem in the application of neurostimulation was the lack of standardized, quantifiable measures for determining the effectiveness of treatment. So I think this bears out in what's available today. The first two indications that are approved for DBS use are Parkinson's and essential tremor. Both of these have a measurable motor state that you're trying to fix. So remember our guy from the earlier video, you can see his tremor, you can measure that tremor. And that stands in pretty stark contrast to something like depression, where it can be nearly impossible to tell if a person's feeling well or depressed, and self-report is unreliable. And even within the other symptoms in Parkinson's, like we talked about earlier, it's hard to tell what's working. And so development along those fronts really comes to a bit of, not, I won't say a halt, but it slows down significantly. All right, so ends our history. This brings me to the problems. Where are we today? And challenge number one is that we need to not only be able to stimulate the brain, but we need to be able to observe the effects of that stimulation on the brain itself if we want to be successful in developing new therapeutics for mental health. So, taking a step further, I'd suggest that closed loop neuromodulation is the key to next generation neurotech. And I think many of the things happening in the market and preclinical and science all suggest similarly. And this really comes down to a principle from control systems, where I'm a bit biased, that's my background, that any system whose state is controllable, by definition, must also be observable. I'm not the first one to invoke control systems in the brain. This is not like an original idea. I'm showing a result here from Danielle Bassett's group. It's pretty incredible, actually. So they show just how much controllability if any given area of a brain exerts on the rest of the brain. And so the generalized version of that's shown on the left, where what area of the brain can steer the system into many different states. And you'll see on the bottom, that's the inside view of the brain. And you see that big red hotspot at the midbrain area. That is DBS, basically. Put a deep brain stimulator down in there, and you can basically cause similar results widely throughout the brain. They're effectively driving these hubs of brain activity that are well connected to the other areas. At the same time, stimulation on the surface cortex has really minimal effect. Like you see this kind of dark blue black area on the top. What I'm showing on the right, modal controllability, suggests what areas can steer the system into difficult to reach states. And now we start to see the inverse, where some of these specific cortical areas on the surface actually have a better ability to do that. So this has real implication for devices like deep brain stimulation and things like Neuralink that are sitting on the surface. So I'm glossing over a kind of lot of beautiful detail in this paper, but the point that I want to illustrate is if you want fine control of a brain state, you also need fine measurement of that brain state. There are some other problems that are maybe a little bit easier to wrap my head around. So disorders like depression, anxiety, OCD, and so on, all these mental health disorders have a few things in common. The first is that the brain networks that represent these brain disorders or cause them, I'm showing depression as an example here, they're widely distributed throughout the brain. They're not localized to small areas like are. They're different between different people, and they change over long periods of time. And that's something that you have to track. And so with this, we can gain a little bit of an understanding of what are the key attributes of the next generation of neurotechnology. If we're going to address these four problems, what do we need to be able to do? There's a few key attributes. First, large scale, the ability to detect and stimulate activity throughout large areas in the human brain, because we know these circuits are all over the place. Next, they should be adaptive. We need to be able to adjust to the user's evolving needs throughout time and without being reimplanted. And finally, we need to maintain the ability to both sense and stimulate brain function, that closed loop I was talking about. The existing technologies that are available today don't really scale particularly well to meet some of these demands. I won't go through each of these four, but just thinking about coverage a little bit, I'm showing today's state-of-the-art implants. So in even the Neuralink, which is incredible in many of its technological areas, you would still need 6 of them to cover just 1% of the human cortex. And despite how incredible that device is, it still has a long way to go. And it's also not surprising that it's at where it's at for those who've been watching, because we have some scaling laws. So this is the closest thing we have to a scaling law anyway, and it's a bit out of date now, and it's from Stevenson and Cording, and I know Conrad has actually given one of these Foresight talks in the past, so maybe we need to invite him to come and give an update on the law here. But this law predicts the number of neurons that we can simultaneously record using electrode-based technology as a function of the year. And the doubling time here is a little over 7 years, and at that rate, to get to the E to the 11 neurons in the human brain, we're well over 100 years, if not longer, from whole brain scale. But even time doesn't necessarily solve it. Electrodes have to invade brain tissue to listen to single neurons. That's part and parcel of how they work. And that means that they cause damage as they enter into the brain. And that results in this really interesting dimensionless number that was given by Marcus Meister called the Butcher number. So this is the ratio of the number of neurons destroyed per the number of neurons that are recorded. So as you can see, the Butcher number for things like the Utah array, like we're using today, is something like 200. Neuropixels gets you all the way down to 2.5. I don't know that we know what the Butcher numbers are for things like Neuralink or Paradromic, some of the new devices coming on market, but I doubt that they're going to be below 1, and effectively they have to go to 0 if you want to scale to the entire brain. So that leads us back to what physical principles do scale in the brain. So let's just look at what physical forces are out there available to us. Light has really phenomenal properties, excellent resolution, but it scatters very quickly, just a few millimeters into the brain. And that means we can't really interact with some of those deep brain structures that we know are so important to the disorders we've been talking about. Magnetics can get depth pretty well, but the physics tell us that these can't be implanted. And as we've seen, electricity is great for listening to neurons, but with the increased risk of bleeding, infection, and an inability to scale, it's a difficult way to get there, potentially a long road. And I don't think the brute force is the right way here. And that leads us to ultrasound. What you're seeing here is not just a cartoon. This is a physics-based simulation where these expanding waves show how we ping the brain to read function with ultrasound, and then how we can focus those beams down and steer them around to then stimulate particular areas of the brain. And ultrasound physics kind of sits in this really nice sweet spot where the waves are just the right size to be very precise, but they're also powerful enough to penetrate deep into the brain. So we get this really wide field of view, check, while maintaining this really precise measurements down to hundreds of microns. We get this over long periods of time. Ultrasound is very stable. And because we're operating at this mesoscale in some of the non-human primate work we did at Caltech, we could train models on day one and up to 2 years later use that same model and it still worked. That's difficult to do on the timescale of even a few hours or days in electrodes, so pretty amazing. And finally, it's minimally invasive. The device sits inside the skull, so it's still an implant, but it's outside of the brain. And that means that you could potentially put devices like this in like a 1-hour outpatient procedure. So what all of this means together is an approach that's potentially capable of whole brain, input, output, sensing brain-wide activity, and reacting to deliver really precise neurostimulation anywhere that's needed. Reading brain states with ultrasound is really possible because of some advances in ultrasound imaging. So the physics were pioneered by one of our collaborators, Mikhail Tanter, in Paris, first published in Nature Methods in 2011, so still a relatively young technique. During my tenure at Caltech, I was responsible for adapting ultrasound for use in large animals and humans for the first time. So in 2021, we published this paper using it to read brain states in real time, which was one of the first examples of an ultrasound brain-computer interface. We have a few follow-on publications from that, one in humans and another one doing real-time BCI that I haven't included here, but let me know if you're interested. The technique itself is called functional ultrasound imaging. It generates signals that are similar to what you would get from a functional MRI machine. These machines are like 15 tons. But here, we're not only getting that with these miniaturized devices, or in our case, it's still connected to a big rack. I'll come back to that in a minute. But these signals that we're detecting are about 10 times more sensitive to brain function than what you would get with fMRI. And they're about 800 times the resolution. And maybe even more importantly is that you can miniaturize this. There's nothing in the physics to stop you from doing that. Unlike an MRI machine, we can also put information into the brain or stimulate the brain. And that would immediately allow us to change function and even rewire the brain over long periods of time. And this can be done by focusing ultrasound waves, delivering energy to any location in the brain with millimetric precision. And in addition to modulating brain function, we can also reversibly inactivate brain regions or even deliver drugs. I'm not going to go into that now, but if you're interested, please ask a question. And these features really form the basis for correcting disease states. And again, I'm including a couple of key scientific advances that make that possible. So that's the science. And on the technology side, building a device like this, an implantable ultrasound device, is really challenging. Luckily, much of the groundwork had been laid for us when we started. So cart-based ultrasound scanners now fit inside handheld devices I'm showing from Butterfly Network on the left here. And today's transducers are small enough to fit on probes the size of a matchstick. And this was just not true even just a decade or two ago. And so these advances really pave the way for implantable ultrasound on chip technologies. And I hope this slide reminds you a little bit of the one I showed earlier, where we had an entire lab being distilled down to a single implant. I actually did not do that on purpose, but after I was preparing this talk, I realized that there were some parallels there. So this actually points to the goals of Forest Neurotech. On the top, or on the left, is the type of ultrasound scanner that's available today if you want to conduct neuroscience research, and similar to what we were using at Caltech. At Forest, we recently partnered with Butterfly Network, the same person that made this kind of ultrasound on chip technology for handheld point-of-care ultrasound I showed in the previous slide. And together, we're developing these miniaturized ultrasound on chip technologies for use in implants for neuroscience specifically. I should also mention that despite the miniaturization, we're not paring back the technology. In fact, that Butterfly chip right there has close to 9,000 channels, which is much more than the 1,000 channels that we have with the Verisonic system on the left. And all the research that we did at Caltech, we did with just 128 channels. So the leaps forward right now in what's available to us, technologically speaking, in ultrasound are pretty large still. Okay, so what does that buy us? What do we actually do with all of this? About 1 in 3 people that have a mental health disorder are also treatment resistant. So what does that mean? They're diagnosed, and after 2 drugs fail to work for them, the likelihood of another drug working drops significantly. But the way our system works, we tend to use 6 or 7 drugs on average before we give up and start to consider surgical options. And as we've seen, today's neurotech is still a little bit out of date, and it doesn't meet the needs of those millions of people that are living with these treatment-resistant forms of disorders. So Forest really hopes to be part of the solution that will bring hope to those patients and the researchers that want to help them. So we're creating this platform to enable researchers and clinicians to directly measure patient-specific brain states, healthy moods, unhealthy states, all while the person's quote unquote in the wild, while patients are going about their daily lives, experiencing all the different stimuli that cause their symptoms to change. In the future, the goal is to empower these researchers and clinicians, and even the device itself, to guide brain states towards healthy patterns, whether that's through a number of interventions at the physician level or directly through the device itself. And the amazing thing that you get, quote, for free from these next generation technologies is that once you access these really large portions of the brain, that enables the study of and treatment of one disorder, but it also means that you get all of the entire host of disorders effectively for free. So no matter the reason that you were implanted in the first place, you get access to everything. And so maybe it's a little bit hokey, and the smartphone should be some kind of VR interface because it's going to take a few years to get there. But at some point in the future, hopefully we'll see this extend beyond severe and treatment-resistant forms of brain disorders, and even into the realm of wellness. Because again, whole brain access means that no matter the reason you were originally implanted, the device can be reprogrammed through software alone to perform these myriad different types of sensing and stimulation. And so with that, I'll pause there and just say thank you. I'm seeing there's a lot of questions in the chat, so I'll try to leave some good time for that.
Wow, wonderful. That was absolutely amazing. I'm sure we have a ton of questions already. Maybe Logan, if you want to kick us up. Or go for it, Micah.
The ultrasound devices, are they able to only read and write to a single location at a time, and then they have to move and read different location, or can they do multiple at the same time?
I think that's to be determined. It really depends on just how much energy you need to deliver to any given space. There's no reason that you couldn't spatially multiplex a phased array chip, focus it here, subset focus there, and you can just do that with transmit delays. You're starting to split up the chip, and so your power, the amount of intensity that you can deliver is going to reduce. The overall aperture may change, which means your focus and your focal gain may change. So there are trade-offs. You're not going to get that for free necessarily, but I think that it's definitely possible. The other thing I'll mention is that typically speaking, the effects that you see with focused ultrasound neuromodulation do last beyond the stimulation period itself. And so you can just, if you need to, temporally multiplex, stimulate here, then stimulate there, and the effect should last throughout.
Wonderful. Next one up, we have Nicholas.
Hi, great stuff, Sumner. Really nice to see you again. I have two questions. First one, in a lot of the schematics examples, you showed multiple chips implanted. Do you think that's going to be a critical aspect to this working, and that the different ones are going to be interacting? Or is that just, each one will be independent, and to get full brain coverage, we'll need to get multiple, but they won't really interact so much?
Yeah, I think it really, again, it depends on the indication of interest.
Mm-hmm.
There are probably some subset of indications for which a single implant would suffice because it's a narrower area. Maybe you don't need the same types of focal gains. You can get away with a bit more narrow beam and a smaller aperture. That being said, my hunch, and this really is just a hunch and an intuition, is that most of the early applications in the next 5 to 10 years are going to require a small constellation of these. Now, we're talking about a few. We're not talking about 20, 50, or 80, right? We're talking about 3 or 4. And that buys you a couple of things. One, it synthetically increases the overall aperture of the device because now you have beams coming from multiple directions. So it's only at the interference of those two beams at the focal point that you actually have this intended stimulation. So you have fewer off-target effects. It also means you can bump up the overall power. So one of the big limitations here is you're implanting something. Putting energy into that device generates heat, and heat in the system is hard to dissipate. So you can spread that heat out and energy out over larger spatial areas and time. So I think that the vast majority early on, I'm betting, are going to need a few.
Yeah, that makes a lot of sense to me. Lots to be gained there. Okay, second question. Do you think you will need contrast agents of any form, or, be it small molecules, genetic encoded proteins, cells that have been engineered, be either, on the effector side or the reporter side? How do you think about, contrast, additional contrast?
Yeah, need? Probably not. Want? Definitely. It opens up the space like in a mind-boggling way, right? The ultrasound platform itself really is a platform. It can enable a whole host of different directions that you can take this. On the endogenous side, so all the kind of work that we had done in ultrasound BCIs, that's purely endogenous. There were no contrast or reporter mechanisms going on in those studies. And that worked really well. The sensitivity is definitely there. So I'm fairly confident on the readout side. On the ultrasound neuromodulation side, the neuromodulatory effects are small, and their literature is a bit more topsy-turvy. I don't know what you want to call it. And part of that is a couple of reasons. One, most of it has happened in animal models, and animal models of the types of stimulation that we're interested in, animal models of depression aren't particularly good. So there's a limitation there. And then when you go into humans, most of the focused ultrasound work has been done transcranially. So you have the confound of the skull, people are using lower frequencies or doing aberration correction, you have attenuation. So there's a number of these reasons to believe that the effects that we see in mammals and large animals may not be as applicable to what we're doing, because once you obviate the problem of the skull and you can work at higher frequencies, better spatial resolutions, everything changes a little bit. So I think there's just a bit of science that needs to be done. It's one of the big reasons that we decided to do this as a nonprofit research organization rather than as a commercial company, because I think there's uncertainty there. I'm quite certain that something will work. It's just unclear which of the many approaches will. Okay, so that's endogenous. Sorry, this is a long answer. If you're willing to change the brain and actually introduce some viral vectors and start doing sonogenetics and have cells that actually express specific sonically receptive whatever, now you've just opened a big can of worms. Within the near future, I think that's mostly going to happen in animal research, partially because the safety profiles aren't well understood. And we've had opto for decades, and it still is, not like something that we're all putting in our brains yet. I think sonogenetics are going to be behind that because it's still just a budding field right now, but it does seem to be working. We have calcium sensors, we have all sorts of things. So we can overexpress the mechanically sensitive ion channels that we would want to make to deliver deep into a large brain like the humans. So there's a delivery problem and safety problem, but give it time.
Wonderful. We have Marcus.
Thanks, Raj.
Thanks for the talk. In our lab, we work on focused ultrasound stimulation, non-invasive through the skull. And we can see effects 1.5 hours after stimulation in humans. So we see faster reaction time, 7 to 8% faster reaction time. One question, you mentioned this technical possibility with the butterfly system. Do you think such a system with arrays of transducers will ever be able to go for the skull as well?
I'm always hesitant with the question ever. Just like long timelines are long. I have concerns. Let's put it that way. Phased arrays that are based, so the butterfly probe, for those that don't know, are capacitive micromachined ultrasound transducer arrays. So these are silicon based, which is why we can bump up the channel count so high. But you're basically layering different metals and oxides, and now you have this well, and this well that's tiny. We're talking about 100 micron. Then you vibrate this membrane with this capacitive force. But doing that, these are very small. So even getting pressures that are similar to today's piezo transducers of the same size is a difficult problem. So maybe we could say that whatever you can do with a phased array, you're probably going to be able to do with a piezo array first. I haven't seen a ton of phased array work in non-invasive. Most people are using big, giant single element transducers that are they're like vibrating like a car speaker. They're huge. It's not to say that it would never be possible. I think there's going to need to be a leap of faith on the technology side, just given the way that CMUTs are fabbed today. I don't know if they get the pressures that you need. I haven't seen a way to get there yet.
Okay. And one second question. So I think a big challenge for implants is really the ethics and, participants agreeing to do it. So if you look at Parkinson's, people are very old, but if you look at mental health disorders, they might be, 20 years old, 30 years old. So they have to live with an implant for a very long time. So we did a survey with 800 participants, 400 patients and 400 healthy subjects. And out of 5 options, implants were the worst option. And also it didn't differ between healthy participants and patients. And participants said safety is more important for them than efficacy. So they don't care whether implants are working better. They just don't want to have surgery. So how do you plan to go through that challenge to convince people, first of all, to convince participants to have an implant, and then to convince ethics boards to have implants in young people rather than old people?
Gradually. The Overton window does tend to shift on these things. Actually, I'm glad that we talked about pacemakers a little bit. I thought I had too much in there, but actually, If you think about it, the idea of putting something inside of you to beat your heart for you, and it's possibly nuclear powered, and if it fails, you die, would have probably sounded crazy. And I would bet if you ran that same survey of participants asking them in 1957 if they want to have a device implanted to beat their heart, they'd say, no, I'm good. I'd rather just something be safe. That sounds crazy. And yet that Overton window has shifted massively. Pacemakers are commonplace. We install thousands of them all the time. I think you'll see something similar here. Now, what does that mean practically? For us right now, you're going to start, like many neurotechnologies do, in non-significant risk studies and prove out that the device has some utility. So these are going to be cases, and there are some cases, where people are already having pieces of their skull removed as part of their standard cycle of care. And when they're already having that skull removed for their standard cycle of care, why not do a little bit of imaging, see what's going on, learn a little bit more about that particular disease state. And again, this is where remote sensing becomes a lot more fun, in my opinion, than invasive implantation. Because now, even if you're studying something, let's say we talked about traumatic brain injury and the kind of Neolithic thing, right? Traumatic brain injury, you're going to remove a portion of skull, and now you can image the brain, but you're in there anyway. And maybe that person has a comorbidity of a particular psychiatric illness. You already have that data. And so this is a spark of what I had been talking about, being able to develop diagnostics, monitoring, and therapeutics and software is you don't need to change the device. You don't need to change the implant location. You get some of that information for free. And that allows you to actually develop early on with no added significant risk some of the efficacy data and safety data that you would need to move into the next indication and the next indication and the next indication. And if you can prove that you do provide some value in a given indication, even if it does add risk, now you can start actually doing that. And of course, this happens all the time. This is how technologies are developed. At some point, you say, I think there's enough proof of efficacy here that it's worth trying. Neuralink just implanted their first subject, and obviously that's extremely invasive. And then this is already being done too. I should mention that there are several studies using deep brain stimulators in an attempt to treat treatment-resistant depression. And in those cases, you are going to someone who is effectively on the verge of suicide every day. And that person, their Overton window looks a lot different than someone with moderate depression in their 20s. But you have to start somewhere. And I think it's just gradual.
Yeah. Okay, thanks.
Okay, awesome. I just want to impersonate the FDA. Are you sure about that? And you're just like, yes, gradually. Okay, wonderful. Next one up, we have Zan.
Hi, it's great talk, and thank you so much for talking about this. Just I've been hearing about ultrasound stimulation recently, and including a device by Open Water, and I think they have a similar device with ultrasound. And I'm just wondering what the differences are in how Forest does it and Open Water, and what's out there beyond even these two groups doing this work.
Yeah, as far as I know, and I don't know a great deal, so if I'm wrong, I apologize ahead of time. But as far as I know, Open Water is developing transcranial focused ultrasound. So this is a non-invasive device. So although the energy that you're delivering is in the same realm, you're talking about physical or mechanical waves, the regimes in which we operate are quite different. So the skull has 3 layers. You have this laminar layer, and this trabecular layer, and another laminar layer. And the trabecular layer has all these pores. You've probably seen like the cross section of a bone before, all these kind of bubbly pores. Those pores are about 500 microns wide on average, which means you need at least millimeter waves to get through them. Millimeter waves in ultrasound world are very low frequency. So typically you're pulsing at 200, 500 kilohertz maybe. We're like the work at Caltech, we were doing it at 15 megahertz. So we're orders of magnitude different. And that means that the resolutions, you're diffraction limited by your wavelength. And so the resolutions are also an order of magnitude different. Your focal spots are going to be different. We also don't have to deal with the aberration, which is the shifting as the wave comes in clean and then hits the bone, it gets like all shifted and attenuated. We don't deal with a lot of that. So I think the problem space is different. The solution space is different too. Ideally, you're not going to wear a giant helmet around every day. So if you're working on a non-invasive approach, ideally, you need to go in for one or a handful of therapies, and then the effect lasts a very long time. But if you have an implant, it's something that you can repeatedly do every hour, every day, whatever it takes over a lifetime. And those use cases are just different. I don't know which indications are going to bear out to be responsive to a single or handful of stimulation protocol versus something that needs to be chronically implanted yet. But it's probably a slightly orthogonal space.
Thank you.
Okay, awesome. Afterwards, we have Logan.
Hello, I see you
Hey, Logan.
again.
You too.
Yeah, so I was wondering about you mentioned, and some of this was covered in the chat, but you mentioned that magnetic stimulation was not preventable. I guess what essentially was covered in the chat was that it's too low spatial resolution, and also the device, physically speaking, the magnets need to be very large, and there's not really a workaround for that. I was wondering, in the case of larger magnets, is it possible to, because I'm thinking more from the perspective of spatially defined inducing spatially defined genetic changes rather than brain computer interfaces. Is it possible to get a focal spot on the millimeter scale using those large devices, or is that still just not feasible?
I'm not sure. Just to clarify on a couple of points, magnetics can refer to a whole host of things. So there's endogenous magnetics, which is optically pumped magnetometry, OpMag, groups like Cuspin, and a few others are developing these. And that is just measuring the natural magnetic fields that are happening because groups of neurons are firing with action potentials that create dipoles that happen to line up more than they don't. And you get these femtotesla phenomena. Unfortunately, femtotesla is small. We live in a microtesla environment of the Earth's magnetic field, so it's hard to measure it without getting into the noise floor. So that's like endogenous magnetics. Second one is active sensing, and that's things like MRI. Now you're actually putting in the B field and measuring the change in spin. And so that's an active form of magnetics, and that's the one where you need the really big magnets. And that's on the sensing side. On the stimulation side, and I didn't actually put it in the talk because it would have just been way too long, but TMS actually has a really interesting and rich history for treatment of mental health. I honestly it pained me not to put it in there because I have done a lot of deep dive on where that came from and what worked and what didn't. And it has a similarly interesting story to DBS. I just didn't have time. But that's a whole other version of magnetics in the brain where now you're actually inducing the magnetic field to cause a localized effect. I'm guessing that's the one that you're talking about, where you want to trigger a spatially local change in some phenomena. Is that right?
Yeah, I'm thinking something like magnetogenetics style.
Yeah.
And just how much spatial resolution could you potentially get in that situation?
Yeah, that's a good question. I don't know. I don't know exactly how tight you could get it. I know the TMS focal points are relatively large compared to ultrasound, but still much more focused than many other techniques. I don't know.
Okay, with looking at ultrasound, I've run into the issue of heating. Localized heating is the way that I was like sonogenetics, and it seemed like the most feasible route for inducing sonogenetic changes in gene expression. And I ran into the issue of that potentially being harmful just due to the heating effect causing damage to the brain and such.
I often find when your nuisance regressor is bigger than your effect size that maybe you shouldn't treat it like a nuisance regressor. If you're inducing heat and it's causing an unwanted effect, maybe investigate the effect a little bit. I actually think that ultrasound-based heating is a very interesting way it's a bit more blunt, right? But it's a very interesting way of modulating brain function. And we know that it works. And in fact, it's, I think, maybe the only FDA approved way of using ultrasound for neuromodulation right now. And Caltech uses it to reversibly inactivate, I think, subthalamic nucleus for temporary reversal of tremor association.
Yeah, I read about that one, actually.
If it works, then they crank the machine up to 11 and ablate that same tissue. Yeah, I won't give up on heating. Heating's pretty cool.
Yeah, I wrote this grant recently, and I've been I got some feedback on it, and I've been trying to contextualize the feedback in the context of, anyway, it's off topic for this, but I'll let us move on to the next question.
I'm happy to make an email into or whatever, help coordinate on the back end. Let's see if we can get at least to one more question in the last minutes. This one is from Steve Potter, and he says, what about interaction with phase-modulated light, photoacoustic tomography? Is that still being looked at?
Oh, yeah. Yeah, there are definitely several groups that are looking at PACT imaging, photoacoustic computed tomography, and other forms of interaction. So for those that don't know, the idea is basically you put in light, and that light will then excite the tissue and actually locally heat that tissue. And the heat actually causes ultrasound waves that then you can naturally detect with an ultrasound sensor. it's pretty cool because you can beat some of the resolution limits that you're held to with ultrasound only. The difficulty is the complication of the system itself. You need to get coherent laser light effectively into the brain. Implantable solutions are probably a very long ways away, but that is a technological problem, not a physics problem, which is a good thing. I would just be totally speculating to guess how long that would take or just how difficult it would be. We haven't done a deep dive on that. But I'm optimistic over the long term that will be a very useful technique.
Okay, we have 3 more questions, but I want to make sure that the final question gets asked, which is always, if people are excited about this technology, which I think they are, how can they help you, Neuroforest, any other projects that you're involved? How can they find out more? How can they, get back to collaborations?
Yeah, get in touch with me. I'm on Twitter at SumnerLN, I think, or you can email me, sumner@forestneurotech.org. Always happy to chat about potentials for collaboration. We're working with surgeons, ideally many surgeons, to implant some of this technology for a wide range of indications. Again, we are a nonprofit, so we aim to enable others to research the things that they are world experts in. The other thing is we are still finishing up our raise, so if you happen to be an ultra high net worth individual or philanthropic foundation, get in touch.
Okay, awesome. We have 3 more questions here in the chat. I'm not sure if we'll get to them now, but can I just ask maybe you guys to reach out to Sumner directly via Twitter? And it looks like we have to have you on very soon because there's a lot of demand for discussion. Thanks everyone for joining. Really appreciate it. Thanks a lot, Sumner. This, I'm sure, will also, again, crack our Neurotech seminar YouTube playlist. And yeah, really excited for what you're cooking up and we'd love to have you back anytime.
Thanks, Allison. Thanks, everybody.
Bye, everyone. Thanks for your great questions.